This extremely good physics book has some extremely good advice about problem solving, which students rarely follow. And it applies to all kinds of different problems, not just physics problems. If you're a longtime viewer, you may have seen an old video of mine talking about how students can learn to solve physics problems without actually learning physics. So students will solve thousands of problems in preparation for a standardized test, but they will walk away with fundamental misconceptions about basic physics principles. I didn't really answer the important question in that video, which was, how can we avoid this result? How can we learn procedural skills and conceptual knowledge at the same time? This physics book has a pretty good answer. Let's take a look at the book's description of the problem-solving process. Now, I'm not going to read everything here. I'm going to simplify the process that they give, and then we're going to focus on the important sentence. Step one is to identify the concepts, right? What are the known quantities? What are the implied quantities? And what are you trying to figure out? Step two is to set up the problem. So you might draw a little picture that explains the situation in the problem and choose equations that you are going to use. Step three is to execute. That is, to do the math to get to the solution based on how you set up the problem. And step four is to evaluate the answer. That is, to see if your answer makes some sense. This seems like the usual problem-solving advice. It's good, but so far there is nothing here that is going to knit your conceptual knowledge and your procedural skills together. The important sentence is in the set up the problem step. So I'm going to read that right now. As best you can, estimate what your results will be, and, as appropriate, predict what the physical behavior of a system will be. This is the key sentence. Notice that it happens after you set up the problem, but before you execute your plan for a solution, before you do any mathematics. What is this direction telling us to do? It's telling us to come up with a conceptual prediction. One that's not based on symbolic manipulation, one that's just based on our understanding of the problem and our understanding of the applicable physics principles. The conceptual prediction comes up again in the last step, the evaluate step. So we're supposed to check to see if our answer makes sense. Well, what is it that we do? We compare our numerical solution to our conceptual prediction. That's what we are supposed to do, anyhow. But since most students skip the conceptual prediction step, they get to their answer at the end, and if they stop to evaluate it, they're probably doing so in a pretty superficial way. Like, hey, my answer is supposed to be positive. Is it positive? Yes, okay, that's great. I'm gonna move on. Now, checking your answer in this way is fine, but solving the problem and then checking to see if your answer makes sense is a completely different cognitive process than making a conceptual prediction and then comparing your numerical solution with the prediction that you made earlier. When you skip the conceptual prediction step and you only evaluate your answer after you've gotten a numerical solution, you are looking for a justification for why that solution might make sense. But when you make a conceptual prediction, you are pitting two models against each other. One is an idealized conceptual model that's based on your physics intuition, and the other is a mathematical model based on the math that your teacher told you to use in situations like this. When these two models are in conflict, you end up learning something. Either the conceptual prediction is wrong and there's something about the mathematics, something going on with the mathematics that you don't understand. Or the conceptual prediction is right and something went wrong with your mathematics. Either you're applying the wrong equations or maybe you made a mistake in the arithmetic somewhere along the way. In either case, you get to improve either your conceptual understanding of what's going on or your procedural skill at executing the mathematics involved. As you solve more problems in this way, you end up knitting your conceptual predictions and your mathematical skills together. That way you don't end up like the students I talked about in the other video who learn how to solve basic physics problems without ever understanding physics concepts. I get into more detail about the nature of problem solving in this video over here. Thanks for watching. I'll see you next time.